Okay, so now I'm going to explain to you the interpretation or computation of like the vector operations from last time using a coordinate system. So what I described to you on the previous video was how to multiply a vector by a scalar or how to add and subtract vectors, and that was all done like visually. And in practice, you want to really work with numbers. So there's a way to do that, which is fairly straightforward, and again, you may have already seen. The idea is that, as I had mentioned before, you can really think of vectors anywhere in space. So in particular, you're always free to move a vector. Imagine that you already choose a coordinate system, right? So you choose a point in space, and you choose two perpendicular lines, and you want to measure all the other points in space with respect to this reference system. So what that means is that if you take a point x comma y, then you can draw a vector that starts at the origin and terminates at that point in question, which is the position vector for the point P. And again, this will be the origin. And there's a useful way to understand this vector, which is as the sum of two vectors, and we know that we can do that already because we already discussed addition of vectors. So you have this vertical vector and this horizontal vector. Okay. Now, what's the size of this segment? This segment has, if you just care about the segment, not the direction, this has size y, okay? And this other segment, notice that you have here a right triangle, this other segment has size x, okay? So what we are going to do is imagine that you have what's called a unit vector. So along the x-axis, there's going to be a vector which is called I. So I it represents the vector 1, 0. Okay, and along the y-axis, there's another vector which is called j, and that vector represents the point 0, 1. So these two vectors will play a key role because the idea is that any other vector can be described in terms of these two, as you will see in a second. So these are called the unit vectors. And so for the sake of the argument, imagine that this had been the point 3, 5. So if this is 3, 5, that means that this segment has size 3. And so basically what you could do is like take the vector I and multiply it by 3, right? And once you rescale this vector I by 3, you obtain the entire pink segment. And so what that means is that this segment really, when it's not 3 but just x, right? This vector, right, is just a rescaled vector of the vector I. And what's the rescaling factor? Well, it's precisely the number x. So you can think of this segment as a vector x times I. And by the same logic, I said, well, this is 3, 5. So if this is 5, that means that, again, you're free to move the vectors around. So you can move this vector j here. And so this has size 1. And so if you multiply this by 5, you reach the endpoint of this segment or of this vector. And so that means that really the blue segment or the blue vector should be the vector 5 times j, or if it's not 5 but just y, it should be the vector yj. Okay? So what I just did is a very fancy way of saying that the position vector is a sum of two vectors. Which vectors? The vector xi plus the vector yj. And if you break this into in a more familiar way, notice that this is just representing the point x comma y. So I'm just saying that the point x comma y can be rewritten as x times 1, 0 plus y times 0, 1. Right, which sort of makes sense because you would multiply what is x times 1, 0? Well, you move x on each entry and you do the corresponding multiplication. So let's just work it out here. So what would I like this to mean? In case you haven't seen this before. Well, the idea is that this is the same as x times 1, x times 0, plus 0 times y, or y times 0, comma, y times 1. And so this is just x 0 plus 0, y. And this is, when you do addition of points, is entry by entry, and so you get x, y. Okay? But now, this elementary operation, we just reinterpret it in terms of vectors. And so the key feature here is that any vector in the plane can be decomposed as a sum of two vectors, one in the x direction and one in the I direction and one in the j direction. So any vector can be written as a sum of two vectors. And if you take linear algebra, what you would actually say is that this vector has been written as a linear combination of the vectors I and j, but we won't use that terminology. Okay, and so the point is that instead of working directly with the pictures of the arrows, you can just work with these points. Okay, and so for example, we can translate the operations from last time into super straightforward operations in terms of their coordinates. So let's do the scalar multiplication. Well, so as I had said before, say if this is a vector v or r, let's for a moment, this would be the vector 2r, right? You preserve the direction and just double the size. But now the way in which we're thinking about this is that now you can move the vector r to the origin, okay? And so when you move the vector r to the origin, you can also move the vector 2r to the origin. So it would be like on top of the vector r. But as you might suspect, if the vector r had coordinates x comma y, the vector 2r will have coordinates 2x, 2y. And so what that means is that in general, the vector lambda times r, which is lambda times xy, is just what you get by doing the multiplication entry by entry. So it's lambda x, lambda y. Okay, and so for example, and so this is the way to do multiplication of a scalar with a vector if you use coordinates. So that means, again, like, what is 2 times 3, 5? That's 6, 10. What is negative 1/3 of negative 1, 5? That's 1/3. Negative 5/3. Okay, and so like the operation is just it's just like doing it at an individual level. This number times this number times this number, and so on. Okay. So doing the scalar multiplication is very convenient from this point of view, and the addition and subtraction also have a straightforward meaning. So again, what would happen when you take two vectors? If you take two vectors and let's call them R1 and R2. Right, if you took two vectors R1 and R2, their addition was this new vector. Now what you would do is move everything to the origin. So let's say here you have R1. That's a position vector which represents the point x1, y1. And well, okay, this is, let's try to do this a bit more. It doesn't matter. It looks parallel to the x-axis. That's what I don't want to see. Let's see. Well, let me redraw them so that it's more easy to see on the board. So you have here R1, and then, well, yeah, let's say now this will look better because it's slightly tilted. That's what I want. I didn't want something that looked completely vertical or completely horizontal. So now in my picture, when you move this here, you get something like this, which is better. Okay? And again, imagine that this represents a point that has coordinates x2, y2. And so, in order to do the addition, you were doing this parallelogram, remember, and the diagonal represented the sum. But really, I mean, like that should not be a surprise, right? Like what you're doing secretly is like taking this x1 piece plus there's a size that has size x2 here. And then you have this y1 piece and then you have this other side, this other piece of size y2. So what I'm trying to say is that when you perform the addition from the coordinate perspective, this point has coordinates x1 plus x2, y1 plus y2. Okay? So again, let me write this here in a more clean way. What I'm saying is that when you add vectors thought of as position vectors, namely that they are representing some point in space, you just do the individual addition or the individual subtraction, right? So it's x1 plus x2, y1 plus y2. Okay, so similar here. So you combine the x's, you combine the y's with the corresponding operation, and it is as if they're not talking to each other, right? Like you don't, in order to know the answer here, you didn't have to look at the answer there. Like they're not interacting with each other. So they're like it's just like doing two separate sums or separate differences, taking the differences between two numbers. So say this is 1, 3 plus 2, 4. This would be, again, you do this individually, so you get 3, 7, or 1, 3 minus 2, 4, and you get negative 1, negative 1. Okay? So this will be, as you can see, this way you can do the computations which were visual originally in a more efficient manner. And like this is the actual point of view that we will take when we're doing any calculations. Okay, so there's not a lot to say from doing scalar times a vector or vector plus a vector. What's more interesting is new operations with vectors that whose analog with numbers is not as interesting. Okay, so this will be some new stuff. What will make this more interesting is that these operations will involve simultaneously both the x and y components. So if you notice here, in order to do this operation, x and y did not talk to each other, right? You didn't care what's going on with the other. The same with the addition and subtraction. For the next two operations that we will discuss, which are dot product and cross product, they're sort of entangled, they are intertwined, so that's what gives a new flavor to this vector perspective. And it's not just like having like a list of numbers that you work on individually. Okay, so I'll explain that in the next video. We'll start talking about what dot product is, how it can be useful, and what you can compute with it.